Alright, so this is part 2 of the review of Chem 151 material for Chem 152. Continuing on with the next section, which is molar mass determination. So what we're looking for here is to make sure that you know how to calculate a molar mass. Again, this is a 151 topic that you should come into this class knowing. I'm going to expect that you're going to be able to do this, but if for some reason it was always something you're a little bit confused about, I'm going to go over it here in a little brief just to sort of fill in the gaps in some areas where you may have missed, or maybe if it was a little while ago before you took a class like this. So they show us how we can get the mass of compounds like ethylene and ethyl chloride and hydrogen chloride by adding up the masses of the various constituents, right? So we'll need 2 carbon atom masses and then 4 hydrogens to get the mass of ethylene. So it's just a simple adding them up after we've multiplied however many are in the formula. So there's 2 carbons in the formula. There's 2 masses of them that need to go into the mass. Now sometimes they'll call these weights, sometimes they'll call these formula weights, sometimes they'll call them molecular weights, sometimes they'll call them molar masses. I typically will call them molar masses, and I typically do this because most often we use these in a unit like grams per mole, and gram is a unit of mass, not a unit of weight, but that's okay. I want you to see all the different terminology people will use to refer to this so that when you comes time to a test, you're not confused if you take something other than my test with different terminology people will use. So sometimes they'll call this MW. Sometimes they'll even go a little sillier and refer to it being in Daltons. It's typically a more biological term, but all those are the same. They all translate into the molar mass, gram per mole, or atomic mass unit mass, depending on whether you're looking at the mass of a single atom or whether you're looking at the mass of a mole of this particular unit in grams per mole. And again, they round these here, but you can get pretty good numbers even with just rounding. So sometimes students, and especially instructors or textbooks, will round these very highly. So you may get very different numbers if you're looking on a table and calculating them, but as long as you're close, typically to like 1 or 2 decimal places, you're good enough. And the point of examples like this is to show that these numbers will be close. Even if you do these yourself with your own periodic table, you'll get numbers that are close enough that you'll be able to get right answers on a test. There are times on a test where you'll be able to just, use 12 for carbon, or use 1 for hydrogen, use silicon, and still get close enough that you'll get the right answer. Now, of course, you should be using a table and getting more precise numbers. That will help you. I guarantee you get a closer answer. But just know that, especially if it's multiple choice, you can get close enough without having to be that precise on your numbers. And remember that a mole, so when we were talking about these as a unit of grams per mole, a mole is 6.022 by 10 to the 23rd power of whatever that unit is. So for the ethylene, the hydrogen chloride, and the ethyl chloride, that's how many molecules there are. But if it was an ionic compound, they sometimes would call it a formula unit, or if it was a number of atoms, it would be a number of atoms. So sometimes I'll refer to this as a mole is this many particles. In theory, you can count anything as a mole. It's just that, it'd be like more than all the microns to Jupiter. It'd be like a crazy amount of anything. It's more than all the grains of sand on all the beaches, okay? So it's such a stupidly large number that there's not a whole lot else you can count with it other than like molecules or atoms or units of something that then scale up to gram and kilogram sized amounts that we can work with in a laboratory. So calculating a molecular weight, okay, or a molar mass. So you see here they use both the term molecular weight and molar mass. You'll note that these are going to be the same number. Sometimes when they'll call it a molecular weight, they want it in AMU. Sometimes they use the unit just U, as they do if you look at the solution here. They just write it U. Sometimes they write that as AMU. That's the same thing. That's the mass of a single molecule in atomic mass units, which you can be converted to grams, but it's another unit of mass that we can use for very, very small things. Usually it's like, or 1 is about the mass of a proton or a neutron. That's typically about how much an AMU is. 12 AMU is the mass of 1 carbon-12 atom. And if you go on to the nuclear chapter, you'll learn a little bit about mass defect and how that can vary a little bit, but the basic idea is still there. So 1 mole of sucrose has a mass of 342.0 grams. And we get that, again, by taking 12 carbons out of the formula, 22 hydrogens out of the formula, and 11 oxygens out of the formula. Multiply them by their approximate masses. They round off to 1 decimal place just to make this really easy, and you can get an approximate mass of 342. And these will be close enough for lab work. I mean, you don't need more than maybe 1 or 2 decimal places, depending on what you're doing. So it's good to be able to sort of get a ballpark number for some of this stuff without having to constantly look to a table. Oxygen's generally about 16, hydrogen's about 1, carbon's about 12. I'm not going to test your ability to do this. You'll be able to do this with a calculator on the exam, but just be aware that you can get ballparks with these if that's something that you prefer. So we also look at converting mass to moles. So if we're given a mass of something and we need to convert it to moles, we can use the molar mass to do so. The molar mass has units of grams per mole. So if we start with grams, we divide grams by the molar mass to get the number of moles. Moles being some number of particle units or whatever this thing is made up of. So typically what I'll tell students in a 151 class is that moles get multiplied, you see here right there, by the molar mass to get grams, and grams must be divided. So that's how you remember. Grams get divided, moles are multiplied. That's how you keep track of which way to do this. Again, this is a simple example. Something on the test may be no more difficult than something like this example. And then 6.6, converting moles to mass. Again, moles are multiplied by the molar mass. So we get the molar mass, formula weight, molar masses in grams per mole. These are the same number. We just add up the masses from the table. 23 for the sodium, 1 for the hydrogen, 12 for the carbon, and 3 times 16 for the oxygens. If you have an algebraic calculator, you may be able to just type that in exactly. That's the kind of calculator I would recommend for this class. So see if you're able to get these kinds of numbers yourself when you do a review. You could even pause right here and see if you can do this yourself and get approximately the same number as what the text has. So you're pretty solid on doing problems like this for the test. Okay, so the next topic is on dilution and molarity. So molarity is moles of solute per liter of solution. So we have some moles of something we've dissolved into something per liter of solution, which is typically water. And we show here a little bit of how we could convert that in different ways, right? So we start with the definition of molarity, and if we multiply the molarity by the liters, by the volume, then we could get moles. And if we conversely then divide the moles by the molarity, we could get the volume. So these three equations, these three ways of working it out can do pretty much any kind of molarity problem the text will give you, or any one that you may see on the test. So here they have an example of calculating a molarity. So they'll get a molecular weight, they'll take a mass that was provided, they give you 2.355 grams of some sulfuric acid, they calculate the molar mass of that acid, they convert grams to moles by dividing. Remember, grams are divided, we get moles, we put those over the volume that they gave us, it needs to be in liters. So they gave us 50 milliliters, and then we divide that, so we get 0.05 liters. It's not 0.5 because that'd be 500 milliliters. And we get an answer of 0.480 molar. And the concentration is typically described as 0.48 molar is typically how they would state that. So this basic workout, if you can do something like this, you're pretty solid with molarity type questions. And then here we're looking at trying to get the moles out of a molarity. So they give you a 12 molar aqueous solution of hydrochloric acid, and they want to know how many moles of HCl are there in some volume of that. So again, we could look back to the equations that we were seeing here. If we take molarity times the volume, we'll get the moles. Again, this just follows with the units, right? Because molarity is moles over some liters. So if we get the liters of solution, so we'll have to convert those milliliters to liters, as they do here, so it's 0.3 liters. Multiply by the 12, cancel those out, we'll get the moles, and it's pretty straightforward. And again, they got a couple more examples in here. These are pretty similar to the ones that we just looked at. I'd focus on the first two. Those would probably be the best. As you get down in here, they start asking about how many milliliters you need and concentration of cholesterol. It gets a little more complicated. So I'd probably stick with the first two. If you can do those in the examples we looked at, we're pretty solid. So let's talk a little bit about dilution, right? So you may have heard that M1V1 equals M2V2, and that's what the text also discusses here at this point. So if you have a molarity and a volume and some change happens to the volume, you can calculate the new molarity under those conditions as long as the moles of solute has not changed. So let's think about this for a little bit. So if I have some beaker and it's at some certain concentration and there's a volume, let's say it's a concentration of 1, and I pour water on top of it that doesn't have any more of the solute in it, I am diluting it by that additional volume that I've added. So now the new total volume is the old volume plus the stuff I added. And so I'll have the initial concentration, the original volume, and the final volume, and I can solve for the final concentration, and that's what they show here. Now, technically, this is done here in molarity, but you can have this actually be any unit of concentration and any unit of volume you so choose. It doesn't have to be liters, and it doesn't have to be molarity. It could be some, as long as it's some concentration unit that could be converted to molarity, it will work. So it has to be something where you have a proportionality that's related to moles, so that the moles stay constant in both situations, then it will work. If you have some kind of mole-based concentration unit or something that could be converted to moles, then this will work. Typically, you'll see this expressed as like a C1V1 or a C2V2. So to express that idea that molarity is not technically a requirement for this way of thinking about concentration. So they say here, I've got 500 milliliters of a 0.2500 molar sodium hydroxide solution starting from a concentration of 1. Okay, so what I can do is plug those in. In this case, my initial volume is the thing I don't need, but you don't have to, actually, it doesn't matter which one you view as the final and which one you view as the initial. As long as you properly pair the volume with the concentration at that time, you'll be able to solve it. So, because in theory, you could run the dilution equation in reverse. There are processes called concentrations where you can remove the solvent without affecting the solute. If you have a process like that, then the dilution equation will still work. So you could technically have something be concentrated. But sometimes those processes destroy the solute, so you do have to be careful. You may not be able to work with like a strict heating depending on what the solute is. But in theory, a concentrating process can also follow the dilution equation, as long as it only really removes the solvent and not the solute, so that the moles on both sides stay the same, as we previously discussed. So here they solve this for some volume initial is equal to the concentration final over some concentration initial. Again, this is just a reorganization. I've divided both sides by the initial molarity. Plug these in and get 125 milliliters. Now we know that this is going to have to be less because we're starting from something that's more concentrated, so that's a kind of ballpark check that they're talking about. We know that the concentration is going to decrease from the initial starting amount. So that means we've added some more volume, so that means that the starting volume will need to be lower. So that's a good helpful point. And they say that it decreases by a factor of 4, the concentration decreases by a factor of 4, so that will mean that that similarly will have to happen to the volume. So that's also what we see going on here. Different ways to think about it, but just make sure that in terms of the direction you're going. So this will be how much you start with, 125 milliliters, and then you'll add the remainder water to reach 500. So for example, you were doing this in like a volumetric flask, you'd pour some in there and then you'd pour the top until you reach the 500. That's the logical way of like thinking about a physical thing you would do that would follow this kind of rule. And so then again, we have two example problems. Again, these may be helpful to you. Answers are in the text or in the outside guide. But if you can do ones like this, you should be pretty solid. And they're very similar to the ones we just did. Make sure that you see, again, when you use the dilution equation, you don't have to worry about converting milliliters to liters as long as both sides are in milliliters. So that's not usually a problem. And then again, we can think about it the same way. I like the first one. The second one gets a little more complicated because they talk about adding acid to water. That's more about doing it in real life. The math works either way you add, but of course. So our final topic here is just on the ideal gas law. So again, this is a 151 topic you may have reviewed. The equation is PV equals nRT, where P is the pressure, V is the volume, N is some number of moles of gas, R is the ideal gas constant that's related to the units of everything, and T is the absolute temperature. They'll often call T the temperature, but I think it's a bit of a misnomer because it suggests that it's a temperature like Fahrenheit or Celsius. It's not. It's a temperature where 0 has to be absolute 0. Typically this is Kelvin, but theoretically any temperature scale where 0 is absolute 0 would work. It's just Kelvin is the most common one. There's another one called Rankins that's for Fahrenheit, but we won't worry about that. The point is that the T here is an absolute temperature. So it can't be Celsius, it can't be Fahrenheit, it must be Kelvin for our purposes here. Key reminder, the units of pressure, volume can be different and they'll change the value of R. Sometimes they'll even do N instead of having it be in moles, they'll do it in like millimoles or something. So in theory, those can be in different units. And R just changes. Like an absolute temperature, if it was in Rankins, it would be different. But the value of R fixes all the units so that all this works out. So it's different depending on the units of things. And that's what they talk about a little bit here too. We rearrange the ideal gas law for whatever kind of relationship or system that we're trying to solve, right? Because it contains all the variables that control a gas's state. We typically will call the ideal gas law, quote, an equation of state, because that describes how it can encapsulate all the properties of a system with just these 5 variables. And in fact, there are other places where the ideal gas law shows up, in the expansion of the universe or in osmotic pressure or at other places where the same model actually works, even though there's no gas. I know that's a little weird, but in this case with an ideal gas, which is what we're looking at here, we can solve this to look for various relationships, right? They say here for like a Boyle's law relationship, the number of moles and temperature have to be constant so that pressure and volume can change inversely. Since pressure and volume are both on the same side of the equation, they are what's called inversely proportional to each other. Variables that are on the same side, of course, are always constant, but variables that are on the same side in the standard way it's written out, where we're not dividing anything, it's just multiplied, are what are called inversely proportional. And variables that are on opposite sides, when the ideal gas law is written in its standard form, where nothing's divided, then those variables are, if they're on opposite sides, they are directly proportional. So if I increase the number of moles of gas, the pressure will go up. If I increase the number of moles of gas, the volume will go up. Okay, if I increase the temperature, the pressure and the volume can also both go up. So those relationships we can see just by looking at the form of the equation. So like I said, in Boyle's law, pressure and volume are inversely proportional. In Charles's law, volume and temperature are the relationship, and in Avogadro's law, volume and number of moles are in the relationship. You don't have to memorize any of these guys' names or what their particular laws are, as long as you know how to derive them from the ideal gas law properly. And again, the typical value for R that we use is 0.082, 058 they have here. Sometimes I've seen it as 0576 or something like that. But the value of R is in atmospheres, liters, Kelvin, and moles. And if we needed to put this liter atmosphere, which actually ends up being a unit of energy, into joules, then it'll be the 8.3145 value. So, and on an exam, I'll typically give you these constants, if I'll note that in advance in the study guide, but you should just know these values. It's 0.082, 058, or 057. Different texts, a little different. Make note, the little variation won't change the answer. Another key thing that might be helpful that they mention in this paragraph is that an ideal gas, one mole of an ideal gas will occupy about 22.4 liters at 0 degrees Celsius and 1 atmosphere of pressure, which is typically called the standard atmosphere, standard pressure and temperature. Now, different fields in different places, sometimes the standard temperature is like 25, but for the ideal gas law, whenever they talk about like a standard temperature, it's 0. Again, different fields, different people. But there they have pressure in pascals and V in cubic meters. They mentioned that's how they get it to be in joules. Those units cancel to joules. But this is typically the form that we'll use for most of our problems. But bear in mind that sometimes we might need to use these others depending on what other units were provided. There's lots of units of pressure like bar and all this, but there's a value of R for all of them. You can look them up if that's what it is that you need, but you should just know this one here for the problems that we're going to do. So we'll do some gas law calculations, right? There's kind of 2 forms of these problems. One where we will rearrange the ideal gas law algebraically to obtain some value that we're missing, right? So if we rearrange the ideal gas law to solve for n, we'll move the R and the T over to the other side and solve for n. Then, because they ask here how many moles of gas. are in the lungs of an average with this lung capacity. Okay, so air typically behaves as an ideal gas. Most gases will behave as an ideal gas as long as they're at room temperature and typical atmospheric pressures. But the key thing for a gas behaving ideally is it's far away from its phase change, so it's not undergoing any subliming, it's not undergoing any condensing, and it's not under any extremes of pressure where it might cause the particles to collide with each other in strange ways. It's not undergoing any chemical reactions. It's able to fully be a gas. Like I say, it's not undergoing any kind of phase change. The hotter the gas is, and the more volume, the less pressure it has, typically the closer these ideal gas law calculations are to real life. But real gases always vary a little bit, but air is pretty much an ideal gas at room temperature and pressure. So this will come out pretty well. So they say here, okay, assume the lungs are at 1 atmosphere normal body temperature. Okay, the air in my lungs might be a little cooler than that because as I'm breathing it in, right? But that's not necessarily a bad assumption. So I have to convert this temperature to Kelvin. So I'll need to add 273 to it, 273.5 if you need a little more precision to get this 310 that they get. This is our conversion factor. Here they use 0.6 instead of 5.8. Again, I'm not sure why they seem to be pulling different ones, but we'll find that we'll get the same answer anyway. 1 atmosphere, 3.8 liters, and we end up with 0.15 moles. Okay, doesn't sound like a whole lot of air, but remember that a mole is a lot. So they say a lung volume of 4 is about 1/6 of the standard molar volume. So yeah, if it was at 0, it would be a little more. And this is an assumption you can sometimes use, that 1 mole of an ideal gas is approximately 22.4 liters. So sometimes that'll help you approximate. In this situation, we have a final and we have an initial. So this uses a Boyle's law scenario. Again, you don't need to identify this with a particular person, but when we have like they have here, a pressure and then a change in pressure and a volume and then a change in volume, we only have these variables changing. So that means that the number of moles and the temperature, of course R is a constant so it doesn't change, will be changing. So as long as these two are fixed, then some initial state is equal to some final state. And I like the way the book writes this out. This is actually, I will say, the first book that's actually written this out in a way more like how I demonstrate this to 151 students, because I always want to join them back to why is this initial state equal to this final state? It's because these variables here stay constant in both cases. They're both equal to the same thing, so they must be equal to each other. That's the logic that's operating here. So we're given they say, an initial volume of, let's say, 1 atmosphere, and then it's going to change to some final volume that is 9.5 atmospheres. And then the uncompressed volume is 410 milliliters. So we'll put that in there as the initial volume, and then we'll be able to solve here for this final volume as the missing variable here. So we've got 4 variables. We know 3 of them. We can rearrange this to solve and get an estimate here. And again, they say the pressure in the cylinder increases about 10-fold. The volume must decrease by about 10-fold. Remember, these are inversely proportional. So what happens to one will make the other one go down by the same multiplicative factor. So if this approximately hit by a factor of 10, then this will be decreased by approximately a factor of 10. So that's a good ballpark. I like these ballpark checks that they have in this textbook. As we move through the course, you might want to look at these too, because having a way to sanity check your answers will help you, especially on multiple choice tests, be able to cross out those crazy answers that they put on there so that you can stick with just the ones that seem right. And sometimes that'll even help you make a good guess if you need to. If you don't have enough time or you run out of something or you're not sure, at least make a guess that's reasonable instead of crazy guesses. And they have an example here with an aerosol spray. You'll need to convert these grams, of course, to moles, and then you'll be able to calculate the pressure in atmospheres using this volume. You'll need to convert that to liters, this temperature to Kelvin. So this is a pretty good example here in problem 9.7. And then in 9.9, they want you to get a final temperature in Celsius. So when you work all this out, you'll need to get this back to Celsius. You'll need to do everything in Kelvin. Don't forget to change these to Kelvin and then change them back into Celsius in order to get the answer. In a 151 class, there are a lot of questions I've seen in their homework examples where they'll want the answer back in Celsius, and sometimes students will forget to do that last conversion. They'll do everything else right. So just make sure you're double checking what the state that they want the answer back in is before you put down any kind of answer. So I like that in 9.9 because it has you have to check that. So that's basically the end of this review. What I'd recommend you do is go back through these two presentations and identify maybe some areas where you had some weakness when you took the previous class, or ones that you just don't remember so well, and focus on those. Pull yourself out the study guide and go through. Make sure that you have a sense of how I've described all the problems, that you'll know how to do those coming up to the exam, and you should be pretty good. All of this material is part of prerequisite for this course, so you should have at least seen it, but just make sure you go back and familiarize yourself where you think there might be some gaps in your understanding. And as always, feel free to reach out to me via email if you have any other further questions or anything else. All right, take care, and thank you for your time. Goodbye.